This is a case-based question from Young's double slit experiment. We know in Young's double slit experiment, there's a light source that illuminates two slits S1 and then S2. The light coming from S1 and S2 interfere and they produce interference pattern on the screen because of superposition principle. So this is the screen, and the distance of the screen from the center of the slit is big D, and then the distance between the two slits is small d. So with this experiment set up, let's read the question. First question, consider the following waves. So there are different waves. Their displacement is given mathematically here. Y1 a sine omega t, y2 is a sine 2 omega t, y3 a sine 2 omega t plus 5, y4 is a sine 4 omega t plus 5 by 2. So now the question is like which of the waves coming from sources S1 and S2 will produce interference? Which pair we have to find out. So we have to remember first like the coherent sources only can produce interference pattern. Coherent means they should have same wavelength, same frequency, and phase difference can be there, or but it should be constant phase difference, because and it should not change with time. So if you see all these mathematically, this is omega, and the second one is 2 omega. So definitely the frequency is different, so they both cannot produce. And in the same way, if you see here, this is 2 omega and this one is 4 omega. So definitely these two also cannot. But the other way we can check y2 and y3, they both have same uh, frequency. There is a phase difference of phi. Okay, that is okay, but it if it is constant with the time, then we can choose that y2 and y3 will produce interference pattern on the screen. So answer is B. Next question. Two light waves of same intensity I naught each, having the path length difference of lambda by 4, emanating from two coherent sources, meet at a point. So we have to find out the resultant intensity at the point. Okay. So what will be the resultant intensity? So for example, if it is our path length difference is 1 lambda, okay, then the phase difference is 2 pi. If path length is 1 lambda, this is actually 1 lambda, then phase difference is 2 pi. So similarly, if you say path length is lambda by 2, then it is 1 lambda, then it is 2 pi. If it is lambda by 2, it will be pi. If it is lambda by 4, it will be pi by 2. So we know the formula. The resultant intensity is 4I naught cos squared phi by 2 if two light sources, coherent light sources, interfere. Then this is the resultant intensity. I naught is the intensity of the incident light. So now we found out phi as pi by 2. So let's plug in here. So you have a 4I naught cos squared pi by 2 divided by 2, which is equal to 4I naught cos squared pi by 4. Cos pi by 4 is 1 by root 2. So 1 by root 2 whole squared. So we'll get uh, 4 no, this is I naught. This is I naught. So it is I naught times 1 by 2. This 2 will go away. It will have 2 I naught. So C is the answer. Okay, let's move on. Vandana performs, I'm sorry. Vandana performs Young's double slit experiment by using orange, green, and red lights respectively. If the fringe with measured in the three cases are omega 1, omega 2, omega 3, please remember these are all fringe width, okay, which we call it as beta. Then which of the following is correct? Okay, so let's see. So we know that beta is actually proportional to lambda. If lambda increases, beta is also increasing. So let's just remember this. This is the rainbow colors: violet, indigo, blue, green, yellow, orange, red. So this way the wavelength increases. If this increases, beta will also increase. That is, here omega will also increase. So this why this is green, orange, and then red. These three only is used, but their order is different. Orange is omega 1, and then green is omega 2, and red omega 3. So red will have more beta. So omega 3 is more, and then we'll have orange, and then we will have green. So the answer should be this. Next question. In a Young's double slit experiment, the slit separation is 0.8 millimeter. Okay, what does it mean? It is D value is 0.8 millimeter. And the interference pattern is obtained on the screen kept at 50 centimeter, which means the screen distance is 50 centimeter. If the first and also bright fringe, first means n equals 1, bright fringe condition we have to use, is formed at 0.4 millimeter, which means x1 is actually equals equal to 0.4 millimeter. Now we have to find out what is the wavelength of the light used. So what is the relation that connects everything? So it is xn equals n lambda d divided by d. So n is 1, lambda we have to find out, d, and then xn, everything is given. So lambda equals xn d divided by n d. Plug in all the values and you will get the um, answer 640 nanometer. Let's see the last question. Consider the effect on the angular separation of the fringes in the Young's double slit experiment. We are going to see now angular separation, that is theta. Now the screen is moved away from the plane of the slits. That is the case 1. Case 2, separation between the two slits increased. Okay, which means here D is increased and here small d is increased. Now we have to find out which options are correct. Angular separation, let's first write the angular separation formula. Theta equals xn divided by d. Xn, if it is a bright fringe, we can write this as n lambda d divided by d divided by d. So d and d will go away. We can write this as n lambda divided by d. So if you see here, angular separation doesn't depend on the screen distance, so which means it remains constant. Okay, so here it's going to, for case 1, it is going to remain constant. Now if the separation between the slit is increased, so if this increased, theta is going to decrease. So if you see, it remains constant, that is angular separation remains constant, but it decreases in case 2. So C is the right answer. Thank you.